Okay, perfect. So, welcome everyone to the One World Mathematics and Machine Learning seminar. Thank you all for joining us. It is my pleasure to introduce and to have Yingzhen Li here from with us today. So, Yingzhen is an associate professor of machine learning in the Department of Computing at Imperial College London. She's also an expert in building reliable ML systems based on probabilistic modeling and representation learning, having spent time in both industry at Microsoft, some research labs like the Aleatoric Institute, and now at Imperial College. With that, we are honored to have her here today to speak about variational uncertainty decomposition for in-context learning. Please take it away, Yingzhen.
Yeah, okay. Thank you for the invitation and thanks for having me here. I've been working on this kind of probabilistic machine learning and this intersection between it and also deep neural network for quite some time. And recently, you've definitely seen this increasing kind of popularity of foundation models like language models being applied to well, almost everywhere. But then the interesting question here is beyond accuracy, right? If we want to pursue for reliability, then we also need to consider some other kind of metrics, for example, like uncertainty estimation. And in particular, today, I'm going to talk about our recent work, which is variational uncertainty decomposition for in-context learning. So just to give you a very quick peek about the result right here. So in the title page of the slide, I'm showing you essentially the decomposition that I'm going to tell you in a moment that we want to estimate uncertainty of a two class classifier on this two-moon data set where we want to not only produce the prediction uncertainty but also decompose it in a way that we can explain the source of uncertainty. And the way we achieve this is actually just via prompting language models. And we can actually do that with some very interesting kind of mathematical results. So this is a work done basically by my fantastic PhD students, Shavindra, Jacob, Filippo, and Wenlong. And if you are interested, so this is a paper published at last year's NeurIPS. So to begin with, let me motivate why we care about uncertainty. This hallucination problem of language models has been talked about for quite a long time, right? Although recently, right, you probably noticed that the hallucination rate of language models has been decreased, but it has never been eliminated. Okay, so there was this very interesting post by OpenAI people that maybe they somehow realized this problem and then they made some claim on these observations. So first of all, hallucination cannot be eliminated because we cannot achieve 100% kind of model accuracy. So this is reasonable, right? But then the researchers from OpenAI, they further says that, okay, so hallucination might not be inevitable, right? Because even when you cannot make 100% correct for every prediction, you can decide not to tell the human user about your potentially uncertain answer if you have a way to estimate the uncertainty of your output before you actually put that to the user. Okay, so this is the motivation that perhaps in these days uncertainty quantification is still interesting comparing to like you just look into quantifying uncertainty for let's say the simple task like reference classification. But what exactly is uncertainty quantification then, right? So there are different approaches, well, in fact, lots of different approaches representing different paradigm of thinking, like frequencies, Bayesian methods, or somewhere in between. So I cannot tell you all of them today, but I'm going to tell you one interesting thing that is related to what we are going to talk about in our work, which is uncertainty decomposition. So, well, you do have uncertainty in the prediction results, right? But people may wonder where does this uncertainty come from? Basically, the source of uncertainty. So there has been quite a bit of discussion about this source of uncertainty within the Bayesian community and also some other non-Bayesian community. especially for those people interested in studying this kind of second order uncertainty or subjective uncertainty. But in the end of the day, there is a popular decomposition framework based on this additive equation. So we can say total uncertainty equals to aleatoric uncertainty plus epistemic uncertainty. So let's think about coin flip as an example. Okay, suppose I have a coin, let's say £1, and then I'm asking you about whether this coin itself is fair or not, or what is the probability of this coin flip result being say heads or tails on top. Okay, right? So, in order to answer this question, you might ask me to provide you some data, right? So, if I only tell you maybe like three coin flip results, then yes, you can use just the frequency of the heads being on top as an estimate of the probability of these heads on top, right? But we only have three coin flips. This means we don't have too much evidence yet, so you will have some uncertainty in terms of estimating this particular probability because you are lacking data. So if I give you more and more coin flips, let's assume I can give you close to infinity number of coin flip results of the same coin. Then based on this evidence, the estimate of this probability of heads will be more and more accurate and you will be more and more confident in terms of this estimate. So you can see that epistemic certainty is something that can be reduced when you gain more and more knowledge or when you have more and more data. However, even if I give you infinite number of coin flip results, I can still ask you this question: what is the next coin flip outcome? Okay, right? So, well, the coin flip result is actually a random event, right? You draw from a binary distribution of some mean probability p. So this means that even when you are absolutely certain about, okay, so the coin itself has 60% of probability being heads, you still cannot be sure about exactly the next coin flip outcome. So this is something called aleatoric uncertainty or let's say data uncertainty. This is due to the inherent stochasticity in your data. This is non-reducible even when you have enough amount of data. Okay, so this is just the motivation, and then we need to find a quantitative metric to actually compute them, right? So one of the very popular techniques right now, in at least in the classification domain, is something based on entropy. So entropy is actually quite a nice measure, at least for discrete variables, in terms of measuring how spread out the distribution is. So imagine you have a say variable of 10 classes, and then you're trying to measure the entropy of it based on the distribution. So the entropy is actually maximized when each of the class are essentially equal probability, and in this case, you are basically the random variable itself is very random, okay, compared to like the other case when if you have a low entropy, then most of the mass will be centered around one class and maybe very, very small amount of mass, probability mass in other classes. Okay, so for those low entropy distributions, the randomness itself is actually lower. Okay, so hopefully we can be more certain about it. So this is the entropy metric that we are going to use in most of our experiments. Okay, so we have talked about uncertainty decomposition and then also the way to measure it. Not yet fully finished. We need to actually talk about how we are going to decompose it and under which framework, quantitatively speaking. So I work on Bayesian methods quite a few times. Okay, so we will work on Bayesian inference in this framework. So essentially, the idea here is you will have some latent parameter theta that you have some prior over it, and then based on the observed data, you are going to compute some posterior updates on that. So this means you will have a posterior distribution of your latent parameter theta given the data. And then in prediction time, the way you're going to perform prediction in Bayesian methods is something called predictive Bayesian inference, which is maybe a little bit challenging integral. But what it says is just saying that, okay, so I have different latent parameters sampled from the posterior, and then for each of the latent parameters sampled from the posterior, I'm going to take the average over it for the predictions. So you can see from this figure, right? So basically, this is just trying to answer what is the prediction distribution of my test output given the test input. But how does that relate to decomposition then? So there is actually one very nice result about decomposition under this Bayesian view. So remember in the beginning, we motivated that we need a metric or we need a measure of uncertainty, and we said we're going to use entropy. So given that in a Bayesian framework, the prediction is done by the predictive distribution here, which hence is integral. First of all, you can definitely compute the entropy of this predictive distribution as the uncertainty measure, where we call it like total uncertainty or total entropy. But then this entropy has a very nice decomposition. You can show that because of this integral here, right, that involves the latent parameter, you can decompose the total entropy or the marginal entropy here as the sum of the conditional entropy and also the mutual information. So here, conditional entropy basically says that I'm going to get say different latent parameters from my posterior, and then for each of the latent parameters, I'm going to compute the corresponding predictor's uncertainty, which is categorized by this entropy term, but with a particular theta, and then you are going to average over, say, theta from your posterior. Okay, so basically, from this visualization that it comes from this paper in 2017. So they tried to apply this approach to image segmentation, where they want to figure out, okay, whether the segmentation result is like certain or uncertain, because you can really think about segmentation as just, putting different labels on the pixels. So it is actually a classification problem. So you can see from the visualization, the aleatoric uncertainty often highlights the edge, uh, right? That you usually should have a higher uncertainty there, because the edge part is sometimes can be, not so clear. But then for the epistemic uncertainty, which are the things that are, reducible when you have more and more data, so this part reflects that in the data set, training data set, you don't often observe some kind of regions like some interesting patterns here, so that they feel this is a uncertain region. Okay, so this is the decomposition result we're going to use. The question here is why that actually works. Okay, so it's a little bit involved, but bear with me. So let's talk about, from the mathematical point of view, what exactly are we trying to compute for aleatoric uncertainty? Okay, so assume that you have a very powerful model. Let's say you trust your model. Let's say you use a very powerful neural network, so that there exists a latent parameter setup theta star, such that the model distribution parameterized by this theta star actually agrees with your underlying data distribution. Okay, so based on this assumption, right? Since we want to compute the degree of randomness as a way to measure the uncertainty in your data, and we already motivated that you can use entropy as a way to measure the degree of randomness, then you can compute the entropy over the data distribution, where by assumption, this is actually the entropy over your model under a particular parameter, theta star. Okay, so this is what we call the true aleatoric uncertainty for this particular prediction. Okay, so this agrees with the data if your model is powerful enough. Let's say you have a super big neural network. However, in practice, you definitely don't know theta star, right? So in practice, you only have observed data point coming from your data distribution, so that you can use them to estimate your theta. Okay, but instead of using a point estimate based on finite amount of data, Bayesian method says, okay, why not maintain a distribution over plausible parameters under your observed data, and then for each of them, compute the entropy, right? So this is actually a Bayesian estimate of the aleatoric uncertainty, this time that we actually want to estimate. So this will converge to the data distribution uncertainty. Okay. Maybe in this case, it's actually I should remove this script D here. But the point here is trying to say that if you have infinite amount of data, then by Bayesian version of CLT, your posterior will converge to a delta measure around the maximum likelihood fit of your model, okay? And then by assumption that we do have our model being powerful enough to cover the data distribution, so it means that under Bayesian CLT, your posterior will converge to a delta measure around theta star, and then this Bayesian estimate will converge to the true aleatoric uncertainty for this particular prediction problem, say predicting y star given x star. Okay, so this is a justification why we can use this conditional entropy to estimate the aleatoric uncertainty. Okay, so we've talked about aleatoric uncertainty, but then what about epistemic one? Okay, so well, the epistemic uncertainty is essentially the entropy minus the conditional entropy, and by definition, this is just mutual information. But there are two ways to actually write down the definition of mutual information. So first, you can imagine that you look at theta, the latent parameter, as a random variable, okay, and then construct the mutual information expression as a expected KL from the posterior after you incorporate the next data points, x star, y star, to the posterior that just condition on the original data set. Okay, so what this basically says here is they want to measure by incorporating one more data point, okay, how big the change is from the updated posterior to the exact posterior, the current posterior. So if, for example, this KL term is very big, right? Then it just tells you that, okay, this data point seems to be very important so that it changed the posterior a lot. So this is the idea that says that, okay, having this data point informs the update for your posterior a lot so that you have a high expected information gain. So this interpretation is actually been widely used in applications like active learning, Bayesian optimization, and reinforcement learning, etc. So you can see that epistemic uncertainty is a useful concept here. But on the other hand, right, so there is another way to write down the mutual information. So this time we are going to focus on y star as the random variable, okay, and then write the mutual information as the expected KL from a single kind of expert prediction with theta sample from the posterior versus the aggregated prediction. Basically, you average over all the predictions from your models sample from the posterior. Okay, so in this case, if the KL term here is big, right? So this basically just says the individual experts they disagree with each other. They disagree with the aggregated prediction. So you can see that disagreement also represents that my model right now is uncertain about predicting the particular output Y star given the input X star. So this idea of disagreement is also being used to motivate these applications to output distribution detection, adversarial example detection, etc. This kind of detection problems using epistemic uncertainty. So I hope I have motivated that these are two terms, aleatoric uncertainty and the epistemic uncertainty are interesting for estimation. Okay, but just also to say that if you're not convinced that you should always use entropy-based uncertainty measuring, you can also do variance. And in the regression problems, people often do variance or standard deviation. And for variance, there's also similar decomposition rule, like the total variance can also be decomposed into aleatory variance and also epistemic variance. Okay, so maybe I can pause for a moment to see whether we have any questions before we go to the real things that we are going to do today for the paper we're going to talk about.
If there are any questions, you can also write in the chat. But maybe I'll just ask a quick question, Yingzhen. So in terms of the entropy-based decomposition, is maybe you'll speak about this in the next section, but I was wondering how um is this often computed outside of categorical settings?
Um, I think in principle you can, right? So usually also in the regression setup, sometimes people do compute this entropy-based
Okay.
metric, okay? But that's usually in the case where you do this kind of Bayesian optimization, sequential decision making, okay? If you only do, let's say, one shot, just trying to visualize the uncertainty for regression problem, usually people do the variance, and that's basically why we also mentioned that for variance, you have similar decomposition rules.
Okay. Thank you very much.
Okay, so maybe I can carry on. Um, yeah, okay. So these are very nice concepts, okay, except that um, previously, if you want to compute all these states, right, you need to assume you have a explicit Bayesian model. Okay, so it means that you need to build some kind of prior over your latent parameter theta and then do some likelihoods, find some way to compute the posterior, and then compute the predictive posterior. Okay, wow, a lot of approximation going on. So there is this entire field of Bayesian computation that tries to solve this problem. But in language model days, okay, so I could just show you a table about many of these, say, public algorithms that tries to apply Bayesian computation techniques to neural networks. Most of them needs running very expensive Monte Carlo procedures. Okay, and also they need to store the posterior distribution over your neural network parameters. So very expensive. Okay, so in the era of language models, it's unlikely that we will soon be able to overcome all these horrible complexity figures and then make basic methods truly scalable. Okay, so we are working on that, but it is not a very near future. So, but instead, I'm going to advocate for another kind of approach where we will build some kind of implicit Bayesian models and tell you in that implicit setup, we can still compute or approximately compute this decomposition. Okay, so maybe let's talk about that implicit setup because we're going to talk about in-context learning. Okay, so I asked ChatGPT what is in-context learning with language models. So ChatGPT says in-context learning is a phenomenon observed in language models where the model can adapt to a new task simply by being provided with examples or instructions with the prompt without requiring any changes to the underlying parameters. Okay, so what does that mean in a mechanical way? So language models, at least for the autoregressive based language models, essentially they are just defining a set of conditional distributions where you condition on arbitrary length of tokens, and then you want to predict the next token. Now imagine you want to actually use language models to solve data science tasks weirdly speaking. Okay, so let's just assume that you have a data set of n data points. Let's say regression, then we will have covariate x and also the output response y, or in classification, y will also be labels. Then you can imagine using in-context learning with language models to solve this problem in this way. You parameterize or you're going to tokenize your covariates as the odd tokens and then your response, y, as the even tokens. So this means you can just concatenate all these tokens together, let's say x1, y1, x2, y2, x3, y3, etc., to make a length 2n sequence. And then you're going to use x star as your 2n plus 1 token. Hopefully, the model now is trying to predict this 2n plus 2 token, and hopefully this will be close to the correct answer that you want for the test time input question X star. So this is our setup. So just to make sure that this is clear, well, in practice, we definitely need to do some prompt engineering. But ultimately, what's happening here is you need to specify a prompt template that can help you put in your datasets to the prompt. For example, you can tokenize the training data set, and then for each of the test inputs, and then you are going to concatenate, let's say, your X into Y, and then prompt your language model in some way. So here we are just showing one example. This is a classification, 2D classification problem where your X, you're going to tokenize it using its coordinate like this, and then you say, okay, output with this kind of label, right, 0, and then you're going to go for a new line, and then this will give you a second data point. Okay, and then you can see that now for the test question that we actually want to ask, right? We want to ask the model to answer in context, what is the label for this particular input? And then you just put in similar kind of format here, and then you hope here the next token prediction will give you, let's say, 0 or 1. Okay, so this is really the setup here. So, I mean, these days you really need to somehow acknowledge that language models can sometimes do quite amazing things. And we essentially just tried out this template for these three kind of spiral data sets. So it has three classes. And then here we are just plotting essentially the classification kind of labels here, where the intensity of the class basically shows intensity of the color shows you the probability, right? And the color just shows you that corresponds to a particular class. Well, I think they work okay, given that you are just prompting language model to do classification. Okay, so there are actually a lot of researchers trying to ask the question why language model can do this. And I mean, there are works that try to say language model implicitly runs some kind of gradient descent. Okay, but another view of this is coming from this kind of definitive view of Bayesian inference. So basically, we have a, sequence of conditional distributions, right? And then if you multiply all these kind of autoregressive distribution altogether, then you can construct a joint distribution of all the y's given all the input x. And as long as this kind of conditional prediction sequence, and the resulting joint distribution satisfy this thing called intractability, then the definitive theorem, basically coming from 100 years ago almost, tells you that there exists a underlying Bayesian model with some latent parameter theta, okay, so that your joint distribution can be formulated as the marginal likelihood of your Bayesian model, so that your prediction can also be done in kind of implicitly in a Bayesian way. However, there is a catch actually, right? So if we believe that the language model itself can perform Bayesian inference, then we want to compute the set uncertainty decomposition to understand where the uncertainty comes from. Either comes from lack of data or it comes from just in the actual inherent randomness. But the model here is implicit. We just know that it exists. We actually don't know how to compute the posterior P of theta given D. And in fact, we actually don't know what this latent parameter is. So one thing I just want to emphasize here is the theta is actually not your language model's network weight. Maybe one good way to make a kind of analogy here is to think about, let's say, language model and our brains. So in some sense, you can think about the actual weights or parameters in your large language models as kind of like these neurons or nerves or synapses in your brain that actually supports the computation, but the language model itself has learned some knowledge from big pre-training. Similarly, just like we have learned a lot of knowledge from our, say, high school, university, PhD, whatever, right? So those knowledge exists in our brain, but it is some kind of latent knowledge that we actually don't know how to explicitly describe them. Okay, so I will encourage you to think about theta in this way. So you do have some latent knowledge in your language model, but you don't know the form of it. But still, we want to be able to compute or somehow approximate this decomposition. And well, it sounds kind of like impossible, but actually it is possible. Okay, so let us tell you how we do that. So the way we are going to construct this approximation or a variational estimator of the aleatoric uncertainty is the following. Before you ask the language model to answer the real question X star, given your context, we are going to ask the language model another question. We call it auxiliary question or probing question Z. And then your language model will give you the answer U, okay, for your auxiliary question Z based on the context. So your language model can definitely do that because this is just the next token prediction. You can compute essentially this P of U given Z and D. And then after the language model answer this probing question Z with answer U, you're going to concatenate both the probing question and also the answer to the context again, and then ask the real question. Again, language model is just parameterizing conditional distribution that allows arbitrary length of input, so you can definitely do it. So this means we can compute the distribution here for answering the real question given the context and also the auxiliary question answer. And then, of course, we can also compute the entropy. We have actually shown that under this implicit Bayesian model setup, this estimation, what we call variational aleatoric uncertainty estimation here is actually a upper bound of the original uncertainty, kind of aleatoric uncertainty estimation here that you want to get. And we can exactly categorize the gap between the variational estimate and the Bayesian estimate if we actually have access to the exact posterior. Okay, so the funny thing here is this result is true actually for any probing question Z. So it basically means that, okay, so we've built up a variational bound that is true for any Z, so why not just try to get the tightest upper bound? So this is just applying the variational inference theory to it. So the way we get the final estimate is we are going to try to do a minimization problem over Z by minimizing this variation estimate. And then once we've got this minimum of the bound, then we can use the additive decomposition rule, right? Because total uncertainty is something that we can obtain very, very easily because we just directly ask the language model the real question. So we've got the total uncertainty. We can also get the variation estimate of the aleatoric uncertainty. Then we just subtract the variation estimate from the total uncertainty. That will get us the variation estimate of the epistemic one. So this also tells you that the epistemic uncertainty we've got here is actually a lower bound of the model's epistemic uncertainty if you actually have access to the exact posterior. So now you may wonder why this is true, right? So in fact, it's actually very simple proof. So think about this kind of implicit Bayesian model setup, right? So it basically says that due to the definitive theorem, your prediction done by your language model needs to go through some internal knowledge or latent knowledge parameter theta. Okay, so it means that when you answer the real question X star, your model will go through this theta parameter to give you the answer Y star. Similarly, when you ask the auxiliary question Z, your model is going to also go through this latent parameter theta to give you the answer U. So by doing this, we actually constructed a Markov chain that connects your real questions answer Y star and your auxiliary questions answer U, okay? And they need to go through theta. So remember from our beginning kind of motivation when we talk about decomposition of uncertainty, right? So if you use entropic-based uncertainty measure, then the epistemic uncertainty is defined by the mutual information between your true kind of your real questions answer Y star and the latent parameter theta. Basically now based on this Markov chain and also based on data processing inequality, we can show you that the mutual information between Y star and theta is greater or equal to the mutual information between Y star and U. And by the way, this mutual information between Y star and U is exactly the total uncertainty minus our variational uncertainty estimate here. So that explains why we can show this is actually a lower bound of the epistemic uncertainty. So a better way to think about the intuition is the following. So you can really think about U as a noisy measurement of the latent knowledge theta. We are asking a probing question Z, and then the model tries to spit out something, okay, based on the question Z, so that the model, U is kind of like a noisy measurement of theta. So it means that computing the mutual information between Y star and U will also tell you something about the model's internal knowledge. However, because U is only a noisy measurement of theta, so then by fixing U, you cannot recover theta entirely. This explains why it is actually a lower bound rather than just the epistemic uncertainty itself. Okay, so I hope this is an interesting kind of explanation to you why this actually works out. But you can see that this is based on an assumption that there exists a underlying Bayesian model behind the in-context learning procedure that you are going to do with the language model. Now, the interesting question here is whether this is actually true. Okay, so well, it turns out not quite. This kind of idea of trying to understand whether language model is trying to do basic inference has been discussed in the literature for quite some times already. So there were papers that says yes, and there were papers says no. But one of the things that people have tried to do is to empirically verify whether some necessary properties of basic inference is satisfied by language models in context learning. In particular, there is this one thing called martingale probability. Martingale property. So the idea of martingale property is something like this, right? So remember our process of probing the language model. So we are just probing the language model with an auxiliary question, but we are not providing ground truth answers to the probing question. So in this process, basically this probing question should not tell any kind of external information to the model how to solve the real question, right? So there's no external information input. So by doing so, right, so you're not sort of like adding information or you're not losing information. So it means that, okay, once I've answered the auxiliary question and I come back to answer the real question, in distribution, the real question's answer should not change. So this is the idea of martingale property. Basically, fantasize the future data should not change current prediction. So there is this interesting ICML paper, okay, that really tries to put this martingale property into test. They ran some kind of Bernoulli coin flip example and then try to estimate some posterior by doing some kind of probing. And their result basically shows that if you have a lot of say context, basically the context length is quite long, then this martingale property seems to be increasingly validated. So at least they show with some empirical evidence that naive prompting of language model does not perform Bayesian inference. Okay, so well, that sounds like a bad news for us, right? So we spent some time to actually tell you there are some nice results about this implicit Bayesian modeling setup. You can still decompose uncertainty in some way, right? But now I tell you this language model is not doing Bayesian inference. Well, I would say that it actually depends on how you prompt the language model. So my personal claim here is that simple prompting of the language model, you shouldn't expect them to do Bayesian inference, but you can actually construct prompt and also this prediction procedure in a way that tries to get to the Bayesian regime as much as possible. Okay, so this is what we actually did in the paper. So remember the idea of trying to guarantee this implicit Bayesian modeling setup is this idea of explainability. So explainability is a sufficient condition to ensure that there is a underlying Bayesian model. So we want to construct prompting and processing procedures to promote explainability for this entire in-context learning procedure. So first, explainability basically just says that if you permute your context in arbitrary way, then it shouldn't change your model's prediction on the test data point, right? So there are some very nice maps to show you that these also translate to these conditional autoregressive distributions, so that as long as you can ensure that when you permute your context in arbitrary way, it still gives you essentially the same prediction, then you are fine. So in order to achieve that, the way we do that is just ensemble with permuted context. So it basically says that, okay, for this particular question X star, we are going to permute our context for L times. And then for each of the time, your language model will give you one prediction, and then we are going to compute the probability, and then we ensemble them. So this is expensive, but you control essentially the error you can accept, right? If you have high computational cost, right? Then essentially you can increase L to basically make it very, very close to say permutation invariant computation results. So this is permutation invariance. And another thing that is, again, about this Montiel property, right? So Montiel property is actually a necessary condition for explainability. So it basically says that, okay, if you compare essentially these two predictions, the first prediction here is trying to say, okay, I ask my auxiliary question, and then I average over all possible kind of answers from the auxiliary questions and also the resulting real predictions. So this is the left-hand side. So this one should agree with the probability of, if I were to just directly ask the real question. So this is what actually Martingale property requires. So in order to ensure that we apply this thing called KL filtering kind of ideas, so we are going to restrict the search of this probing question Z to ensure that these two distributions are not too different from each other, and we use KL here just because it is convenient. We haven't investigated other kind of metrics, but it works well for us in practice. So this is just to show you the actual procedure. So we are going to choose a candidate set of auxiliary questions. And then we go through this interesting procedure of first asking these auxiliary questions and then append in these answers to the context, ask the real question, and then you compute all these required entropy terms for you. And then we do this KL filtering by throwing away the auxiliary questions that you don't have this Montiel property approximately satisfied. And then we are going to get the, say, tightest upper bound of the aleatoric uncertainty using the remaining or filtered questions. So now you may ask, how do we actually choose these Z candidates? So, well, we have tried different techniques. For example, like we just randomly pick these questions in the X domain. So if you are in the regression setup, then it just says that you just randomly sample from the X domain. So you can also say I define some kind of neighborhood of my real question X star. So in regression, you can say this is probably like the L, some epsilon L2 ball. And then you're going to search your auxiliary question Z within this neighborhood. Well, you can even just repeat the question. Well, in this case, for repeating, right? Because you only ask one question, then we don't do the step 5. But we found that in practice, it works surprisingly okay. We also tried the more sophisticated methods like Bayesian optimization. Well, you can of course spend a lot of compute if you want. So yeah, so this is also, again, just to remind you, right? So we are not really doing anything like writing say hard code codes. We are really just prompting language model, but prompt language model in the way that we mentioned. Okay, so yeah, so as promised, I'm going to show you some examples, right? So at the beginning, I showed you these you know, uh, 3 spiral classification problems, and we prompt quant 2.5 14 billion parameters model to try to solve this problem in context. So while the language model gives okay prediction results. But then we are also interested in how certain or how uncertain the model is in terms of the prediction. So we computed the total uncertainty based on this entropic metric, and then we also compute the decomposition based on our approach. So you can actually see that these two plots show some differences. So the aleatoric uncertainty are mostly around essentially the decision boundary. Okay, as you can see that this actually represent the inherent randomness or inherent ambiguity. But the epistemic uncertainty is mostly high when you are away from the observed data, representing that you don't have observed data or you don't have too much observed data in that region. So you can do the similar thing with regression. So in regression case, we can compute variance or you can compute entropy. I think in this case, we compute variance. So in particular, for this 1D regression problem, we construct it in a way uh, that in this region, the kind of output noise, the ground truth output noise is actually small, but then in this region, the ground truth output noise is actually high. You can see from the data point here. So the idea here is to test whether the language model and also our decomposition procedure can actually capture different amount of aleatoric uncertainty in different regions rather than just doing just the usual kind of homogeneous or noise assumption in regression problems. So if you look at the decomposition figure here, where the gap between the blue curve and the pink curve shows you the epistemic uncertainty, right? So first of all, in the part when you have less amount of data, the data here is actually shown in this vertical bars. In the region when you have less amount of data, then you can see the gap actually increases. Okay, so showing the good purpose here. But also, if you look at the pink curve, the aleatoric uncertainty in the right region here is actually higher than the aleatoric uncertainty estimated on the left-hand side and also middle. So this actually shows the language model somehow capture or understands, okay, this region is noisier than the other regions. Okay, so you can also ask the question about essentially, okay, whether we can apply this to language models, and that goes back to our kind of beginning motivation, right? So at the beginning, the OpenAI blog post mentioned that you can eliminate hallucination by say declining to answer your questions or abstention from answering. So the idea here is the following. So if you can compute some uncertainty measure on your answers, then before you actually output the answer to the users, you can define some threshold. And if your uncertainty metric is actually higher than that threshold, then your model is going to say, okay, I don't know. I will abstain from answering you the question. So how to evaluate the effectiveness of this procedure, right? So you can compute essentially the accuracy of the questions that actually being answered, meaning that you only compute the accuracy on the, questions where language model does not abstain. So this is how we evaluate the result here. So we used our approach to estimate the total uncertainty and also the decomposition approach to estimate the aleatoric uncertainty. And then we put some kind of thresholds. I think we are trying to achieve some kind of false positive rate 5%, or I can't remember, but we put a threshold to these uncertainty metrics and then do the abstention. So if you can look at this kind of question answering benchmark by comparing just the model's accuracy without this filtering approach and also the other kind of approach after the filtering, you can see that the answer, accuracy of question answering is increased, and actually this filtering approach with the aleatoric uncertainty is actually performing a bit better than just using the total uncertainty. So lastly, we can also use uncertainty for decision-making tasks, and this is actually why the Bayesian people are interested in estimating epistemic uncertainty. So there has been some, researchers, for example, like these researchers from, I think Microsoft Research in New England, that they are interested to test whether language model can do, say, decision tasks like bandit tasks. Okay, so the setup here is the following. So imagine you're going to a game arcade center, and then you have a bunch of these crane machines, and because you only visit the game center first time, you actually don't know which crane machine seems to be the most lucrative one. So you have some budget. You can actually play each of the machines for a few times, and then you make some estimate and make some guess about which machine seems to be better, and then play that machine more and more. So this is the idea of say multi-arm bandits. And the way we are going to solve the problem is this UCB algorithm. So we are going to maintain some mean estimate of the reward for each of the action, as well as the uncertainty estimate for this reward for each of the actions. And then for every time, we are going to select an action based on this UCB acquisition function that is a mean plus some scaled version of standard deviation, and then we are going to get a reward from the environment after this action, and then we use this reward to update the model. Now, what we can do in context is we can actually provide, for example, like this action reward sequence as the context to the language model. And then either you can ask the language model to directly predict what is the next action to take, or you can ask the language model to predict if I do this action, what is the reward I'm going to get? So we are going to do the latter approach, and we are going to use this latter approach to enable UCB with language models. So here's the result. So we compare essentially different ideas. So I think the first two methods here are basically UCB based on just count-based uncertainty. And greedy just says that I play a bunch of machines randomly, and then I just figure out the best machine. I just continue playing the machine. So instruction baseline is this paper that they just directly ask the language model, given the context, what is the next arm to play? So the EV-TV method are basically our approach where the policy is computed using UCB, but the uncertainty, basically the standard deviation, is computed either using epistemic variance or total variance. So we can actually show that in the case when this aleatoric uncertainty is actually different across different arms, we can show that the method with epistemic variance is actually performing better comparing to like using the total variance. So the metric here is basically just the regret, so lower is better. So we actually visualize here, perhaps an example why this is the case. So we show here essentially during time for this particular run, right? During time, how many times does the algorithm choose to play a particular arm? So hopefully, right, if you have a good working banding algorithm, during time, your optimal arm, in this case arm 4, will get increasingly being played, and this is the case when we use epistemic uncertainty. But when we use, say, language model in context learning UCB with total uncertainty, at least for these trials, right, you can see that it actually didn't recognize the arm 4 as the optimal arm and actually start to play other suboptimal arms. So this results in higher regret. Okay, so I think that's it. So basically, today I motivate to you, right? So why this uncertainty decomposition is actually interesting, and in particular in the language model setup, where we are actually now in this implicit kind of Bayesian model setup, how you can still perform this uncertainty decomposition, and we show you some interesting visualization and applications. So we are actually very interested in this line of work, and we are continuing developing this approach, trying to extend that to different uncertainty metrics, and also like see whether this can be applied to a non-Bayesian kind of belief update setup. So I'm happy to answer any questions if you have.
Thanks so much, Yingzhen, for the very nice talk. We really appreciate it. We have a few minutes for questions. Please feel free to put the questions in the chat or just unmute and speak. And maybe I'll get started just as people ask a few questions. So, well, one question I did have in particular about the exchangeability. Um, So you mentioned that so LLMs won't, in general, they don't satisfy this exchangeability by construction. Um, but and so there's this averaging operation using the ensemble in order to with a permuted context in order to resolve this. But I was wondering, in principle, the transformer architecture can be independent of the exact positions of all of the tokens. So this is often feels like that when we add in things like positional encoding,
Mm-hmm.
it this is what leads to no longer having the exchangeability of the tokens.
Mm-hmm.
And I was wondering if you just saw potentially just a way of enforcing this w by construction by changing around the positional encoding.
Yeah, that's an interesting question. I think indeed you have a point that you can indeed do some even say it's just the structural design of your network to at least ensure permutation invariance. And in fact, works in this kind of say tabular data domain. So there has been this increasing popular kind of framework called tabular domain, this tabular PFM. Okay, so they actually try very hard to enforce this kind of implementation invariance, somewhat hard coded or hard baked in their architecture. However, in our setup, right, we are interested in using a pre-trained language model and then just do the in-context learning. We are not changing anything in terms of its parameters. So it means that, well, we need to work with their limitations.
Of course, that makes sense. Uh, thanks, Yingzhen. And then maybe I'll also ask, so you mentioned at the end that one of the kind of current directions is in terms of faster prompting algorithms for scalability. Can I ask what is the current bottleneck, do you think, in the terms of the scalability? Is it just having to use a lot of samples of Z, or is it something else?
Um, well, I would actually say that the limitation is actually this permutation, to be honest.
Mm,
Okay, so search itself is definitely also very challenging, right? But unless you are doing this kind of Bayesian optimization way, otherwise you can always fix a budget. Let's say at the beginning you only ask 10 or 30 questions. Okay, so that part is more or less controllable. But really, this permutation part is something that is less desirable from the computational point of view, but that's unfortunately things we want to need to work with. So that's basically why we are interested in like these behaviors of belief updates in a non-Bayesian way, right? So we are interested to see that, okay, so if you don't enforce this right? So what would be the results? Right, so you can still run our algorithm for sure, right? But what does that mean in theory?
makes sense. Thank you. Um, okay. If there's no other questions from the audience, I just want to Um, thank Yingzhen again very much for the your time today and for giving us this very nice presentation. And you have your email there, so folks, please feel free to reach out to Yingzhen if you have any other questions. Thank you again, and we'll see you all at the next seminar.
Yeah, thank you for having me.